So this next section that we're covering, actually I jumped ahead and I went sort of to the conclusion, and it has to do with something called electrolytes. And electrolytes are solutions that can conduct electricity. So like, if you ever seen one of those horror movies where somebody throws a radio in the bathtub and they get electrocuted. The reason they get electrocuted, although Mythbuster says it won't happen, but the reason it's supposed to happen in the bathtub is because there are electrolytes in the water. So what are electrolytes? Electrolytes are ionic compounds or compounds that produce ions in solution. And we classify, and then the ions in solution are what carry the electrical charge. So, and that's how they get the name electrolyte. So when you take, for example, Gatorade, right, and you're drinking Gatorade and you're getting potassium, some sodium, and chloride and things like that, those are actually electrolytes. And those electrolytes are used to carry electrical signals in your nervous system. So pure water by itself doesn't conduct electricity, and it's called a non-electrolyte. And most molecular compounds are non-electrolytes. Now, if we're talking about salt solutions, okay, or acid and base solutions, there's a couple of different kinds of electrolytes. So pure water, molecular compounds in general, there is one important exception, we'll get to that, are non-electrolytes. Now, let me define these down below, and then we'll go up and look like how we can tell whether or not things are going to make ions. But strong electrolytes make many ions. Weak electrolytes make few ions. And non-electrolytes, like water, make no ions. When either they're pure or when something is dissolved into them. Now, the reason this picture is over here is if you have electrolytes in solution, you can carry an electric current, for example, in water and light a light bulb by plugging it into the water. Okay, so let's go back and talk about how we know when something's going to be an electrolyte. And it boils down for ionic compounds. So this is for ionic compounds. It boils down to whether or not the ionic compound is soluble. Is it soluble? So, for example, if I take, this is formaldehyde. When I take formaldehyde, formaldehyde doesn't have a metal in it. It has this structure that looks like this, and you don't need to know that structure yet, but you'll learn how to draw it eventually, right? So, but we generally abbreviate it as CH2O. If you had a container and you had water in it and you put some formaldehyde in it, the CH2Os would stay together like this, and they would float around inside that H2O as a homogeneous solution. So they'll dissolve, but they won't break up into ions. When you have ionic compounds that dissolve, okay, generally it's a metal and a nonmetal, then what happens is if I take sodium chloride, for example, and I put it in water, the sodium ions will separate from the chloride ions. Now, the solution will still be electrically neutral because compounds are electrically neutral, but when it dissolves, it creates this soup of ions. When you put electrodes in there to run electricity, the positive ions go to the negative electrode, and the negative ions go to the positive electrode. So they move towards what they're attracted to. And this is what gives us conductivity in solution and causes ionic compounds to be electrolytes when they dissolve. So how do you know when it dissolves? Well, you could do basically the experiment that we did in the video earlier. You could just try dissolving in water. If you put it in water and it dissolves, then it's forming ions. That's the way that works, okay? Just like the barium chloride or the sodium sulfate, when in solution, they become associated with the water molecules and become homogeneous and make that homogeneous solution. Now, beyond that, though, what most people rely on, they don't actually sit there and try everything out. People have done this for years, and they've come up with a set of solubility rules, and this is what you get on the test. So you'll have this handy in the important informations or the helpful information sheet for exam 2. You'll have something very similar to this. It tells you when certain things will be soluble. So let me explain to you how this works a little bit, and then we'll just do some examples. That's the best way to learn. It says most of the compounds, right, containing the following ions are soluble. So these are the solubles. These ones are the insoluble. So if you have OH, generally you're not soluble, and you won't dissolve, or you'll be a solid in the solution. On the other hand, if you are soluble, then you'll dissolve, and then you'll form an aqueous solution. You'll break up into your ions. Okay, so you could think of these as generally being aqueous and generally being solid in water, okay, not dissolving. So let's look at what it says here. It says lithium, sodium, potassium, or ammonium ion. If you have any one of those ions, you're soluble, and there's actually no exceptions to those rules. If you have nitrate or acetate, there's also no exceptions for that. So every compound that you see in this class containing, this is group 1, ions, ammonium, nitrate, or acetate, those will always be soluble. So they'll always be aqueous, okay? On the other hand, chloride, bromide, and iodide are generally soluble, except when they're paired with silver, mercury, or lead ions, and those tend to be insoluble. So the exceptions in this case would be solids, right? And the exceptions below would be aqueous. So there's things that are usually soluble and their exceptions are insoluble, and there's things that are insoluble but their exceptions are soluble. Now, it seems like that might be kind of confusing, but if you look at this, for example, sulfate, when SO4 minus pairs with these, then it's insoluble, right? So that's another important one. And that's the one we did. There's barium sulfate, right? That's the one that we did. That was a solid. But you notice the exceptions down here. So if you have a hydroxide or sulfide, those tend to be insoluble. But if it's with group 1, right, that first rule, these are soluble. So this rule is super important up here, right? This one, there's very few exceptions to, especially none in this class. And then these ones are generally insoluble, and the only time that they're not is when, again, they're with these compounds, okay? Now, this term slightly soluble, right? For many purposes, these can be considered insoluble. Slightly soluble means it dissolves a little bit, okay? Now, let's go through and we'll practice here, right? So we're going to look at sodium sulfate and barium sulfate and just apply the rule, and then I'll let you do the next two, okay? And then we'll come back and we'll talk about it. So sodium, right? Well, let's see. Well, that's right. That's that group 1. That's sodium ion. And these are generally soluble. So when it says which of the following are soluble, this one's soluble, its state is aqueous. Which means when it goes in solution, it'll break up into the 2 sodium ions. This is the one we did actually in the video, and a sulfate ion like this. Barium sulfate, right? You go to barium sulfate. And there's your sulfate. You're looking at the anion. For most of these, we're looking at the anion. And when it pairs with barium, it's insoluble, right? This is the one we just did. So this one would be solid, right? And so when you put it in water, it just stays as barium sulfate. So this is what I want you to do is, again, you'll do calcium carbonate and potassium phosphate and determine whether or not they're aqueous. And if they are soluble, right, if they are soluble, then write out the ions that it forms when it dissolves in solution. I'll pause it, and when we restart, I'll have the answers already there. Okay, so this is what we have. Calcium carbonate is a solid. If you look at carbonate, which I highlighted in yellow up here, right, calcium is not an exception. So anything in this side of the list is solid or insoluble. So that's S, and so it doesn't break into ions. And then potassium phosphate, Right, phosphate is generally insoluble, but potassium, that group 1, right, is generally soluble. So it's aqueous, and so you can break it up in 3 potassium ions and a phosphate ion. Now, one other class, and they don't really talk about it much in this chapter. You'll notice I got this from 14.3 in your book, but I thought I would point this out now. Um, there are a handful of what we call strong acids. Now, acids, if you remember, are molecular compounds. So, for example, HCl, there's no metal in there, right? So it's a molecular compound. But when you take HCl and you place it in water, what acids do is they'll form ions like this, okay? Now, strong ions will completely dissociate and produce lots and lots of ions, right? So if I have an HCl, every bit of HCl that goes into water, because the water is so attracted to it, will split up into hydrogen ions and chloride ions. So it turns out strong acids are also strong electrolytes. And it turns out weak acids are not the strong acids. So the way you have to do this, or to learn this, is to recognize that the weak acids are not on this list. This is the list from your book of the strong acids that you need to know. Okay. Again, weak acids, not strong acids. Okay. Don't split up. 100. Well, let's say it's split up just a little bit. I was going to say they don't split up 100%, but that's very complicated. Only ionize. That's what we mean by that, is split up partially. And so these are weak electrolytes. Now, in chapter 14, we'll cover some weak bases that we don't talk about in these chapters. But there are some weak bases that are also weak electrolytes. The strong bases are like the soluble hydroxides, like sodium hydroxide, potassium hydroxide. Those are all strong electrolytes.